Good afternoon, or good evening to those of you in Europe, and good morning to those of you in Australia. Welcome to the closing plenary session of the ESIG 2020 Fall Technical Workshop. I'm Charlie Smith, the Executive Director of ESIG, and I'll provide a few brief opening remarks as our Fall Technical Workshop draws to a close. Our workshops are planned with the input of our ESIG Offerings Committee, chaired by Bethany Frew of NREL and Julia Matoiva-san of ERCOT. The committee consists of the chairs of our 6 working groups and several of our board members. We have a great set of volunteers who make ESIG what it is, and we encourage you to become involved if you're not already. Regarding logistics, I would ask you to note that this final webinar will be an hour and 15 minutes long, unlike our previous webinars, most of which were only 1 hour long. We'll have 4 individual presentations of approximately 10 minutes each, and we plan to hold the questions for a 15-minute Q&A session after the last speaker. As we're doing with all of our webinars now, we'll be using the Slido platform for managing the Q&A. We would ask you to use Slido for your questions, as you will not be able to ask your questions through WebEx. You should go to slido.com on your device and enter ESIG12 as the event code to ask your questions. Please be sure to indicate the person to whom you are addressing the question. The instructions are also in the background slide for the webinar, and you will be reminded by the session chair. You'll see a thumbs up button next to the question on Slido to allow you to vote on prioritizing the questions submitted. And that's all I'm going to say about voting. So please keep the questions coming during the presentations, and we will address them at the end. Recognizing the limitations of a webinar with typically more than 100 people on the lines will be muted. So again, we ask you to use the Slido platform to ask your questions with ESIG12 as the event code. The closing plenary today deals with the status and prospects for renewable generation and energy storage technologies. These are the foundation for the energy system transformation which we are undergoing. Looking at a future where most of our generation will likely be coming from renewable energy makes this a critically important topic. The session will be chaired by Alejandro Moreno of DOE and co-chaired by Nick Miller of HickoryLedge. Alejandro serves as the Director for the Water Power Technologies Office in the Office of Energy Efficiency and Renewable Energy at DOE, and also heads up the department's cross-cutting Energy Storage Grand Challenge. Nick is a well-known figure in the industry who spent his career with GE Energy Consulting and is now enjoying his time in private consulting. Alejandro and Nick are frequent and active participants in our ESIG activities and good friends of ESIG. Alejandro and Nick, we appreciate having you here, and I'll now turn it over to you, Alejandro.
Terrific. Thank you, Charlie. Hopefully everybody can hear me and see me now.
Yeah, we can hear you.
Terrific. Thank you for inviting us, and thank you for the entire ESIG team. As Charlie said, I'm Alejandro Moreno. I am the Director of the Water Power Technologies Office in DOE. For those who aren't familiar with it, we lead the department's research on hydropower and pump storage, as well as marine energy. I will say I am one of the people leading the Energy Storage Grand Challenge, not the sole lead, luckily. I am very excited to be able to wrap up this somewhat unusual Fall 2020 technical workshop, and really grateful for an incredible slate of panelists that you'll hear from in a second. These are people with really, truly world-class expertise in the technologies that, if current trends continue, as you heard from Charlie, are really likely to drive the future of the power system and quite possibly, as we heard throughout this session, the entire energy sector. You all heard in the opening plenary, if you can remember that far back, visions for what the grid may look like in the future from a system perspective, really in particular from the University of California's 2035 report. And you heard the sense of urgency in getting there, obviously, with 2035 as a date. We heard from Amal Fadki, for example, that 90% clean energy is possible without coal or any new gas, and really at a cost that's lower than what we see today, but also that business as usual won't get us there. And we heard from Michael Boyle a number of specific policy and institutional suggestions that could accelerate that transition and help. We also heard from Paul Denholm of NREL about some of the challenges of then getting past 90%, that last 10%. Both his confidence that short-term and diurnal variability are problems with pretty clear technical pathways, to be solved, but seasonal storage perhaps isn't. But we also heard an important reminder that that last 10% of capacity is always expensive, even if it's not renewable. I'll say myself, as somebody who spent a good chunk of time working in Africa where that last 10% is often short-term diesel contracts, I know he's not kidding. And we also heard from Mark O'Malley about the value of working directly with system operators and making sure they have opportunities to hear from each other and learn from each other across the world. In the 2 months since then, we've really heard from a truly astounding number of the world's leading experts about many of the specific technical and regulatory challenges in front of us, from grid-forming inverters to hydrogen pipelines, and the work underway to address them. Today's session is going to bring us back now to that same high-level perspective as the opening plenary, but from a slightly different perspective. We'll look towards that same future that you heard about that was outlined back in September, but instead of from the system perspective, now we're going to look at it from the perspective of the 4 primary technology classes that will help get us there, will help get us at least to that 90%. So wind, solar, batteries, and pump storage and hydropower. You'll hear from each of today's panelists about where they see each technology headed in terms of cost and maybe more importantly, in terms of the characteristics and services that it can provide to the grid, capabilities, limitations, and how that's likely to change over time, and what are the R&D challenges as the goal of technology development moves away from simply driving down LCOE in isolation and more towards how each technology can play and provide maximum value through a highly variable, renewable-based power system. As Charlie said, we'll shoot for 8 to 10 minutes of presentations and save a little more time for discussion at the end. Please do ask your questions on Slido. We're equally lucky to have my co-moderator, Nick Miller of HickoryLedge, to moderate the questions. We will, of course, take questions from all of you, but if you're a quiet crowd, anybody who knows Nick knows he won't hesitate to jump in with questions of his own. So without further ado, I'd like to introduce Paul Veers. We'll talk about wind power. Paul is an NREL Senior Research Fellow and the Chief Engineer for NREL's National Wind Technology Center. For 12 years, he was the Chief Editor for the journal Wind Energy and was awarded the European Academy of Wind Energy's Scientific Award 2016 for his leadership. Paul, the floor is yours.
Well, thank you very much, Alejandro, and thank you, Charlie. I hope you're able to see my screen now. Let me know if that works.
That's good.
Okay, thanks. So just to give you a little background on wind, it's a joy to be on this panel, try to represent some of what wind is and does. I think we've all seen these charts that kind of look backward in time for the technology and to where we've come to today. The story of wind is a fantastic story of bringing down the cost of energy dramatically over the decades. And that has fed forward into very high penetrations now relative to what they were at the beginning. Right now, wind delivers about 5% of the global electricity supply, and that percentage in the U.S. is about 7%. That's done with a 650 gigawatt of total installed wind in the world. So it's about 2/3 of the way to getting to its first terawatt of installed capacity. And in the U.S., we just passed a milestone where we're past 100 gigawatts of wind now installed in the U.S. Of course, this really is achieved by cost. If you look at the Lazard analysis of unsubsidized cost of electricity in the U.S., you'll see that there are really three suppliers of electricity now that are competitive with each other, and those are wind, utility scale PV, and combined cycle gas. And wind among them actually can deliver electricity at the lowest cost of any technology now on the grid. But there is a fairly sizable band of cost, and that's because the wind costs are very sensitive to the quality of the resource. Very good wind resource can give you a very low cost, which means that when installing wind and looking for the best opportunities, there has been a drive towards those good, really good resource areas. And that leads to some development of wind where there's already a fair amount of wind involved. In the U.S., that's really a substantial resource in the Great Plains area. There are now 3 states in the Great Plains that are already well over 1/3 of their total generation coming from wind power. That's Iowa, Kansas, and Oklahoma. And perhaps the bigger story about wind development is the state of Texas, where although it's still less than 20% of its total electricity, there's over 25 gigawatts of wind installed in the state of Texas. If Texas itself were a country, it would be number 5 in the world in total installed capacity. Of course, this means that there are already locations, even though the U.S. is only at 5% of electricity from wind, there are places where there is congestion due to the level of wind installation in a specific spot. And that's starting to show us a little bit of a precursor of what we can expect as we install more and more wind on the grid. So I'd like to share the visual that Mark Ahlstrom has put up to kind of give the sense of where this pushes us. Because today, with small amounts of wind in total on the grid, it's essentially asked to deliver bulk electricity. It's an energy resource for the grid. But as we move to higher penetrations, that will shift. We'll be looking at requirements for wind plants in the future to continue to supply low-cost, very low-cost electricity, but they also have to deliver the system assets, attributes of capacity credit and system services. So let's look at these a little bit. We can look at the resource in a little different way than we have in the past. You're probably familiar with wind resource maps that show the total wind speed asset at different places in the country. Well, we've used the wind toolkit capability that has time of day and seasonal wind resource to look at what that would look like to the utilities locally in terms of capacity credit. And they've developed this capacity credit map of the western United States. And a couple of things come to mind. First of all, the dots are existing wind plants. And you can see that there's very little correlation between the location of those plants and the higher capacity value locations on the map. That has not been a driver in the past. The second thing to notice is that there are some fairly high capacity credit locations available that we can start to move to, certainly along the Front Range and in eastern Colorado, Wyoming, New Mexico. But what really stands out is the offshore resource. So there's a huge 50% and greater, 60% and greater capacity credit available if we can develop that resource, which pushes us towards a certain kind of technology solution. That water is very deep. You cannot put in traditional bottom-mounted wind in that area. It's going to depend on development of low-cost floating wind turbines to really exploit that resource. And the other thing is that the location is a bit remote. So it's going to require additional transmission in order to get that resource from where it is to where it needs to be. But the opportunity is there for a wind plant by itself without additional assets to really do an important or provide an important contribution to solving some of the duck curve type of issues that have come up in California. If you look at then system assets, system control, Clyde Loutan gave a presentation a few weeks ago during this workshop where he showed the results of a campaign that was executed with a 331 megawatt plant in California, using that plant to deliver a variety of system services. And they showed that this plant could deliver ramping both up and down very accurately. It could do automatic generation control and stay within a 2% error bound. And it can provide voltage control and frequency control both up and down. So there's already the ability of these wind plants to deliver things that are going to be necessary more broadly. One of the issues, of course, is that to deliver these attributes, the wind plant has got to operate with some headroom. You're going to have to back off from the available power to a lower level in order to deliver the grid attributes. And the question comes up of who pays for that lost revenue. How do you compensate a plant that was designed and financed with the expectation that it would deliver all the power that's available at all times to running in a different mode? Critical question to ask. So what if the wind can deliver the capacity credits and it can deliver some of the grid attributes, people have suggested that, well, we really don't have any research left to do. In fact, I was at a meeting not long ago where the vice president of a grid operator suggested that we really have no research left. So I get this question often enough that it was important to actually convene a group to document what it is that we really need to do, what are the key problems that we have to solve for wind. So we gathered a group, we hunted down the grid experts where they could be found, and we came up with a report that summarized this and an article in Science that would say what it is that we need to do. And I think one of the key findings of this group is that the wind approach to delivering electricity is really a systems approach, more so than any other generation technology that we have. It really depends on energy driven from a global scale of the motion of the atmosphere, all the way down to the scales of fluids that interact with the boundary layer of the airfoil. And the time domain is also huge. It ranges from years of prediction of the total energy output, so you can finance the plant right down to operating the grid at the sub-second. So these requirements force the grid technology or the wind technology to not be able to really make huge progress anywhere unless there is a good link to the other aspects of the total system. So one of the visuals I also like to grab is from our moderator, Nick Miller, who talks about the new grid and the fact that this new grid is going to force the way the technologies have to respond. The old grid was all about inertia, big rotating machines, delivering stability to the grid through their mass. The new grid is going to be about interconnections that are smart, and they're through inverters and have to be told what to do. So although the wind plants now can deliver all the attributes that Clyde showed that we could do, the real question is, when do you ask them to deliver that? How do you operate the grid where in a way that you have to tell each attribute or each asset what to do and when? And these are not just the wind assets, but the solar and the storage assets. When do you add to the storage? When do you take out of it? When do you ask a plant to do the ramping? When is its resource going to be adequate to do the service? So the integrated control is really a big issue. I just like to show one hint then of what goes on. We've looked at wind plants, and these are maps of wind turbines in a wind plant. The arrows show on the left what the sensor on the individual wind turbine thinks is the incoming flow direction, and then it seeks independently to point the wind turbine into that flow. The example on the right suggests what we could do if we aggregated all that information from the sensors and then estimated what the flow direction was and fed that back to the machines. You'd see a lot of error, a lot of the confusion around how each machine should operate itself is taken care of, and you get a much better energy output from a plant like this. This is just a hint at the kind of control that you might think about with the grid as a whole. Don't think of these as wind turbines, but maybe each one is a separate plant, some solar, some wind, some storage. There may even be demand side management assets involved, and the controller has to take the data from them all and optimize that whole system. And one last example I'd like to show that kind of points into the future. We, at my home office, the Flatirons campus at NREL, which is a kind of a remote site, which has some PV installed, some wind installed. There's some buildings on site that have a load. We have a large battery system storage capacity. We had handed to us an opportunity to operate as an island when the single point of contact with our grid blew up, and we had a failure at our substation, and that pushed the Flatirons campus into an island. The research staff there thought, well, if we're handed a lemon, maybe we can make some lemonade, and we can control this microgrid completely off of a renewable set of resources. And they showed that it could be done. We've got about 2 megawatts of generation. There's a 1 megawatt hour battery system, and the load on the site runs about 0.2 to 0.3 megawatts variably. So they were able to show that they ran completely on renewable assets for about a day and a half, had a seamless transition back and forth from the emergency generator into the renewable system, and actually did a black start also off the renewable assets only. So it kind of gives you some hope that there's motion into the future, but certainly these are just baby steps into the kind of things that we're going to have to do. So with that, I think I will attempt to hand control back to you. Thanks.
Thank you, Paul. Speaking from the hydropower perspective, maybe welcome to the club of supposedly mature technologies that get asked why they still need R&D. Sincerely, it's interesting to see a lot of the parallels there from a system perspective and in a grid services perspective that we see as well, and a lot of the same needs. Now I'd like to turn it over to Becca Jones-Albertus to talk about solar. Dr. Jones-Albertus is the director of the U.S. Department of Energy's Solar Energy Technologies Office, where she's in charge of all of the departments, solar PV and concentrating solar thermal power research. Dr. Jones-Albertus has spent her career advancing solar technology from fundamental research and development to manufacturing, and she's held a variety of both technical and leadership positions in the industry with a wide range of patents and publications to her name. Becca, over to you.
Thanks, Alejandro. It's my pleasure to be here and talk about things from the solar technology perspective, although, again, then you'll see a lot of parallels with what Paul just talked about in wind. But for the last decade, it's really been transformative for the solar industry. Back in 2011, DOE set cost targets for what we thought the different sectors, which are shown here, utility scale, commercial, and residential, what costs would be needed for solar to hit to unlock these different sectors. And what we saw over the decade was just really rapid falling in costs, with room for these costs to continue to decline. So in the utility scale sector, we saw costs fall by more than 80%, hitting our targets 3 years early. They were 2020 targets. And in the commercial and residential space, we saw costs falling about 70%, didn't quite get to the targets, but still really tremendous declines in costs. At DOE, we've been looking at and benchmarking costs as they would be if they had no subsidies, like the investment tax credit, and if they were in an average area of the country that didn't have, had sort of average sunlight. But when you think about the costs that we're seeing that are getting reported today, they're much lower, and that's because they take advantage of the investment tax credit, and they are typically in very sunny locations. So in terms of the PPA prices that we're hearing reported, those are all the blue dots on here. Some of them have been below 2 cents a kilowatt hour. We're sort of benchmarking about 2.5 cents today as what's typical. So again, just a dramatic reduction in costs over the last decade that's been really exciting, and which that's coupled with policies and incentives and targets has enabled really tremendous growth. Over the last 5 or 6 years, solar's been about 30% of all new electric generating capacity that's been added to the grid, with wind and natural gas being the other dominant share, and has enabled solar to grow about 50-fold in the amount of generating capacity on the grid over the last decade. Solar today supplies about 3% of U.S. electricity demand, and about 60% of those systems are utility scale large PV systems, with about 40% being residential and commercial scale systems. About 2% is concentrating solar thermal power. And on the distribution system, these commercial and residential systems number about 2.5 million, so they are significantly impacting the distribution system as well, how it operates, its challenges, and there's opportunities with that as well. But deployment in solar, like we saw for wind, has been far from uniform. So while generation overall for the country is at about 3%, we have a few states that are 13 and 14%, and California leading the way with about 20% of its electricity that's generating from solar. And when you get to numbers like 20% and higher, you can start to see some challenges that we have to deal with on the grid. The left figure shown here is the very well-known California duck curve. which shows the net load on the system after the solar resource is subtracted. And of course, what you see with more and more solar is the mismatch that you eventually get between when we have sunlight and thus solar power and when the load demands are on the grid. And this causes operational challenges. It makes solar, in effect, reach economic limits if we don't either couple solar with energy storage, or, which we're doing to a much lower extent today, but I think there's tremendous potential in the future, better couple with flexible loads that can be shifted in time to better match when we have a solar resource. So both of those things are become increasing considerations as we put more solar on the grid. And then on the other side of things, on the right-hand side here, when you have, say, 20% of your energy generation annually coming from solar, obviously sunlight is not 24/7, so that means that instantaneously you can have much, much higher penetration of solar on the grid. And so the figure on the right here shows for 4 of our systems that have the highest wind and solar penetration annually, what it looks like in the orange bars in terms of the instantaneous, the highest points they've hit, between 60 and 80% of the generation for particular moments in time has been just wind and solar, so primarily inertia-based resources. And, as Paul talked about, primary inverter-based resources, not inertia-based, inverter-based resources. And so, as Paul talked about, this is a different operating regime for the grid. And as we install more and more wind and solar, we're going to have more of these moments in time that are going to become more significant. And for the grid to maintain its stability and reliability, we need to have wind and solar that are actively contributing to the stability of the grid. So as with wind, solar plants can support grid reliability, and show here a nice study that was also done by CalISO in partnership with First Solar on a 300 megawatt PV plant, showing that plant could provide automatic generation control or follow an automatic generation control signal very accurately, could control its ramp rate, provide voltage control, frequency response. All of these grid support functions could do very well. But yet, again, similarly to wind today, there's no financial incentive for solar plants to provide these services, and there is every economic reason for them to maximize their energy production. But we do need to start getting that experience operating those systems. So we know we can do it, but there's engineering challenges as we start to do so. And so DOE is investing significantly in research to help investigate these challenges. Chile has also now has the first solar plant that's going to be actively participating in the grid services market, so we'll get some information there. But that's a really exciting area of work and somewhere where obviously we need to just get more experience and solve the engineering challenges that are there. I also wanted to talk a little bit about opportunities, and in particular, opportunities that can come from having 2.5 million solar generators connected to the distribution system, in addition to growing numbers of energy storage, primarily battery storage resources. So this is our sort of solar-centric view of the modernizing grid. And when you put lots of generators on the distribution system, you do fundamentally change with two-way power flow how the distribution system operates, and that has its own set of operational challenges that we're solving as we get into it. But in addition, there's opportunities. Having all of these grid-connected generators offers real opportunities, I think, for resilience. And in particular, in the event of an outage that takes out the bulk power system, we're looking at ways that we can harness these generators to bring back segments of the distribution system and power critical loads while we wait for the outage to resolve and power to come back on. This takes not just solar, but also energy storage, other distributed energy resources. But it's a really exciting area, kind of future-looking resource, and I think illustrates the potential that's possible with the changes we're seeing on the distribution system. So not just with backup generators, which are typically tied to their own individual loads, but having all of these grid-tied generators on the system. And I'll just end by saying that this is just the beginning. So I think, one thing that all the projections show is that solar, like wind and energy storage, is projected to grow significantly over the coming decades. For solar, what we've seen in the past is that all of the projections year over year, they're always too low. We see more and more installed than being projected. So perhaps we can consider future projections equally conservative. This figure is just showing EIA's projections for capacity additions over the next several decades, and they're projecting that solar will triple its capacity over the next decade and reach 17% of U.S. electricity by 2050. There's some huge levers in terms of storage deployment, solar deployment, and one of those big ones is energy storage. The more flexibility we have on the grid, the more energy storage there is, the more valuable the solar generation, and the more we expect to see solar deployed. So there's some really fun synergies between our technologies today. And with that, I'll hand it over to talk more about energy storage.
Perfect. Thanks, Becca. You stole my segue into Babu, but it does show us just how much these technologies are integrated, and they do. The future will rely on not just one, but on all of them upholding and achieving their potential. Next, then, to talk about batteries, and I'd like to introduce Babu Chalamala. He is the manager of Energy Storage Technology and Systems Department at Sandia National Laboratories. As an IEEE Fellow, Babu currently serves as Vice Chair of the IEEE PES Energy Storage and Stationary Battery Committee. Babu, over to you.
Thank you, Alejandro. It's a pleasure to be speaking this session. Thank you, Becca, for the intro for the importance of storage for the grid. As we look at the grid and where we are going, and the storage is going to become critically more important. Just to put it in perspective, we roughly have a terawatt grid in the U.S., and the amount of storage you need to have, to do lots of things in the grid as you go towards a future grid with potentially fossil-free generation, is significant. How much storage we have right now is pretty small, about 2 gigawatts of grid connected storage, and about 22 gigawatts or so of pumped hydro. I mean, that's, in the big scheme of things, amount of storage we have is very small. Storage is just getting started. I think, it's pretty early for large-scale storage in the grid infrastructure. As we move forward, I think, the future looks pretty promising. But to put things in perspective, I just want to give you a sense of, what are the different battery technologies we have and where they are, and what are the challenges for some of these, and what things needs to happen to make storage relatively cheap, safe, and cost-effective. So if you look at the mature battery technologies, you have the lead-acid batteries, roughly 150 years old technology, sufficient manufacturing capacity all around the world. We produce roughly, I would say, 350 gigawatts of production globally. And prices have come down more or less, this is very mature, and 2% increments is a good thing in this technology. Traditional lead-acid batteries, probably $100 a kilowatt hour, industrial grade more. And then for long duration, deep discharge type applications, then you're looking at advanced lead-acid batteries, primarily lead carbon batteries. Those tend to go towards $300 or so. So for the lead-acid batteries, even though it's a mature technology, lots of applications in telecom, backup power, automotive, SLI, industrial markets, you still have challenges to get deep discharge. Can these assets operate for, let's say, 10, 20, 30 years? That's a challenge, because most lead-acid batteries, if you do deep discharge, they tend to have maybe 1,000 cycles at best. Even advanced lead-acid won't give you a lot more than that, but that adds a significant cost to it. And then you have the lithium-ion batteries. This is a 50-year technology, starting in the early 70s. Now it's fairly mature for a number of applications, especially in consumer electronics. That has been a driver in the beginning. Now with mobile devices, and the EVs are catching up. So a lot of the capacity coming online globally is primarily driven for EV applications and for the mobile. And energy storage for the grid is kind of piggybacking on the technology platform. So the application space for energy storage for the grid for the electricity markets and for the EVs is very different. I mean, for grid applications, you need deep discharge cycle life. And if you are building electric vehicles, 1,000 cycles of deep discharge is sufficient to give you 80,000 mile warranties. So we have a challenge in how do you make lithium-ion batteries last longer, operate in deep discharge mode for, let's say, 5,000, 10,000 cycles. So we have ways to go in making lithium-ion operate for a lot longer time. The other thing is there is a worry about safety of lithium-ion batteries. That's a challenging problem. But again, we are learning how to operate this system safely and reliably using power electronics, engineering, and other things. As we look at where this technology is going, I think there's lots of things happening in improving the energy density, primarily using different chemistries and increasing the voltage of the other cells, and potentially we can come down to maybe $100 a kilowatt hour. Okay, and going below that will be rather challenging, mainly because 80% of the cost of typical battery is bill of materials. So there is not much to squeeze. So you can increase the energy density, and that requires some level of bringing new materials technologies into the mix. That's one. And also looking for different kind of chemistries, lithium sulfur chemistries, lithium metal. Those open up higher energy densities for these technologies. So things are happening in lithium-ion space. I think it's pretty promising. And then there are emerging technologies which are potentially cheaper based on low-cost active materials. For example, sodium sulfur, which is an old technology. Lots of installed capacity in Japan. Almost like 4 gigawatts of capacity installed in Japan. But there's not much of a scale right now. It's high temperature chemistry. Can we get these cells to operate from, let's say, right now, 300 degrees or so to maybe 100 degrees? That opens up, engineering space to reduce the cost of the overall systems. The interesting part of some of these technologies, like sodium sulfur or sodium nickel chloride, is that the active materials are relatively cheap and abundant. So $4, $5 per kilogram for sodium and sulfur. But we have a long way to go to reduce the temperature from 300 to something more reasonable in the 100 degrees range. Then you have a lot of interest in flow batteries. You hear about flow batteries as being an exciting new area that provides the freedom to separate energy and power, but it's not really mature yet. The other thing is most flow batteries are not as energy dense. I mean, typical flow battery system, vanadium flow battery system, maybe 30 watt-hours per liter. That's 5-10 times lower than a typical lithium-ion battery system. So increasing the energy density is important for flow batteries. So there's lots of work going on in getting new electrolytes, and you need to get the manufacturing scale to be able to decrease the cost. I mean, if you think about all the flow batteries that we have in the grid right now, less than 200 megawatts maybe, so it's not at the scale. Then you have other interesting technologies. I mean, alkaline chemistries like your AA cells. I mean, this is an old technology. The challenge has been how do you make this fully rechargeable? And the bill of materials for this is probably in the $10 range for a kilowatt hour, and your alkaline AA cells fully manufactured presently for primaries is about $20. That's what you can buy in the store. How do you get this to fully rechargeable and that can operate for a longer cycle life? So there has been lots of interesting work, starting with some of the early ARPA-E funded projects. Now they are becoming commercial. And now it's all about, can we improve utilization of zinc? So it can we make the rechargeability of the manganese side? And can we manufacture them in scale? So if you can get this technology into full-scale manufacturing, and the potential for a bill of $50 a kilowatt hour aqueous battery technology is real. I mean, aqueous is really significant because, then you don't have to worry about safety aspects as much compared to, let's say, organic-based electrolytes. Then you have other things happening in a number of ways. Lithium sulfur, lithium air, those all show a lot of promise, but still pretty early. And sodium-ion battery analogs, just like lithium-ion batteries, but sodium is the shuttle, and that can reduce the cost of lithium-like batteries and using the same manufacturing platforms. And then looking further out, all solid-state batteries that are more safer and increase energy density. So things are happening, I think, in the battery storage technology space in multiple fronts. And the goal is, can we get to technologies that can reliably get us to a lot lower than $100 a kilowatt hour with possibly in the 5,000 to 10,000 type cycle life. So those are the challenges. I think some of the challenges can be overcome incrementally, but some I think need fundamental advances. Now, looking at batteries, we tend to think, people say, okay, the batteries is $100 kilowatt hour lithium cells, but that's not always the full story. I mean, you're building a system. The system is going to be starting with the battery packs, then engineer the storage modules and integrate with power electronics and the energy management systems, all these things to bring a commercially viable project, right? That adds cost. I mean, typically, if you look at from cell to a fully installed system, it'll probably go down from maybe 3 to 4x by the time you're fully installed, and there is not really a whole lot of standardization at this point. So integration costs are significant. So the big savings are not just in the cells; it's in the systems and the integration. I mean, that's not happened yet because we're just beginning to build this industry. This is the early time in storage. Then on top of that, you have range of technologies, different cell architectures, going from cylindrical, prismatic, bipolar, in the case of flow batteries, then different chemistries. You have aqueous chemistries, non-aqueous chemistries, then you have flow batteries. Then some battery technologies need thermal heating, some need cooling. How do you manage thermally to get the kind of cycle life you're looking for? Then you have to worry about the operational safety of large-scale storage plants. I mean, another thing is, how do we build a plant? If I have to design a plant, let's say 100 megawatt plant, to have a modular architecture to build those plants? Or is it for power applications or energy? I mean, that changes what kind of chemistry can I use. And can I do the module and scalability on scales that make sense for the grid? I mean, can I scale from kilowatts to megawatt hours, both in energy and power? And what kind of engineering do we have to do? Then on top of that, cycle life is real issue because if my battery operates only like 5,000 cycles instead of 20,000 cycles, then my project cost is going to be significantly higher. So those are all the things I think we are just beginning to start integrating storage at a scale that makes meaningful sense, and the cost advantages haven't really come down yet. We have a long way to go to really truly get the cost structure of these technologies to become cheaper. So. And just to give you a sense of where are the prices and what kind of cost structures we can look in the next 10 years or so, DOE has been doing energy pricing survey for energy storage systems. So this is from data from 2019 survey. We have done the survey with about 77 roughly OEMs and integrators. And as you can see, for energy applications at a megawatt size to 100 megawatt size, $1,200 is probably looking like real. Okay, but if you're looking at power applications, it's still about $1,000 a kilowatt hour. So it's relatively expensive from where we need to go, and that's the case for either lithium ions or flow batteries. And the question is, what does it take for us to get down even further? So I think it's a scale, that is the cost, standardization, and all those things. And finally, if you look at where we are as an industry, we still need to further improve both in cost and performance. I mean, performance through energy density, cycle life, and all those things, safety. One area is, in addition to lower cost, we need longer duration storage. That's a real gap. We don't have any technologies that can go beyond maybe 8 hours, 10 hours, even flow batteries. So you have something that can give us days to maybe weeks to seasonal storage. What are those? I think that's a major gap we have. And we haven't built large scale storage systems in the hundreds of megawatt class, not as many. So we don't have those learning yet. So for large transmission applications, a lot of applications are going to need large scale storage systems in the 100 megawatt class. So that's an area we need scale. We still need to improve safety and reliability. I mean, it doesn't, as you probably know, you might have heard about all the battery fires in Korea and in the US in the last 1 year. That's a challenge. I think we need to learn how to improve the safety of battery storage systems. On top of that, storage as an asset is new for most of the grid operators. We don't really have a good business models, operational tools, we still don't know how to use storage in the grid infrastructure, both from a regulatory point of view, and the business models are just evolving. And we need to get to a larger scale in deployments so that we have all the issues around bankability, warranties, performance guarantees, managing the risk. Those kind of, taken care of. We are pretty early right now. And then, just like in the PV industry, in the wind industry, we need to come to standardization of equipment, permitting, construction processes, building plants. So this deployment of storage has to become pretty routine to realize the full cost advantages and also, move the technology forward. With that, I'll stop here. And I want to mention that, DOE has identified energy storage as a grand challenge. That gives you the kind of problems we are looking at. I mean, storage is important for the future, but I think, we have technical challenges that we need to overcome to fully realize the costs and bring storage to scale. Thank you.
Perfect. Thank you, Babu, for a very thoughtful and comprehensive overview of really what's many different technologies with different roles to play in the system and different challenges that they each potentially face. Now I'd like to turn it over to David Havard from GE Renewable Energy, who will talk about hydropower and pumped storage, effectively moving from a number of the storage technologies that are on the horizon to the storage technology that really is dominant today. I do want to say before introducing David that, back to what I was saying at the beginning, the notion of these mature technologies that don't have growth is, I'm as guilty as anyone of sort of not understanding that sometimes, and I was surprised this year, even though I managed the pump storage research in DOE, when I found out that over the last 10 years, there's been about as much new pumped storage put on the grid in the U.S. as all other storage technologies combined, just from a couple upgrades in plants. So without further ado, I'll turn it over to David. David Havard is the head of project managers in the hydro business of GE Renewables, where he assesses market needs, prioritizes technical developments for hydropower technology development. He joined the hydro industry 11 years ago and is an active contributor to forums on hydropower as a panelist and author. He's currently also one of the vice presidents of the French energy cluster NREL, which is concerned with the energy transition. David, over to you.
Thank you very much, Alejandro, and thanks for the opportunity of being able to speak to you all in this interesting workshop. I've got 10 minutes, and in those 10 minutes, I hope that I will convince you that there's a lot going on in hydro, and that hydro is very relevant to the renewable transition that we've all been just talking about. If I start by just giving you a quick view of something that you know pretty well already, it's the hydro fleet in the US, which is built from conventional hydro and pump storage hydro, has been mentioned. It's about 10% of the capacity of the overall generation in the US. A few key points I'd just pull out. First of all, 30% approximately of the conventional fleet is run-of-river, so let's call it intermittent hydro, which means that 70% of the conventional and the bulk of the pump storage is pilotable. It can be adjusted, it can be dispatched in line with grid requirements. Another key point is the longevity of hydro installations. They do last typically over 100 years. So it means that 80% of the US fleet, having been built since the 1950s, that fleet's still there contributing in the 2050s. So it is relevant now, it's relevant in 2035, it will be relevant in 2050 and even beyond. We are, of course, talking as well of units which are synchronous units. And I think it's a theme in the workshop that we've seen in the various calls about the transition between synchronous generation to inverter-based generation. Paul mentioned it as well. I think it's an interesting point. But nevertheless, there will be this synchronous capability for some time to come. The other thing I just wanted to highlight is when we say energy storage, it contains the word energy. And I'm at fault, and I think that collectively we're at fault. We often count it in terms of power, and we talk about gigawatts. So there's 24 gigawatts of pump storage, as we've noted, in the United States. If we look at it from an energy perspective, And there are one or two extreme installations which really boost this figure, but it's 3,366 gigawatt hours of storage. And if we just take the closed loop facilities, there's 57 gigawatt hours there, with an average of about 8 hours of storage. So there's a significant amount of storage already contributing to the energy transition, and I'll come back to that point a little bit later. We've also got some numbers here comparing capital expenditure costs. There are some numbers that are internal to GE Renewables. Those are the numbers that you can see, and I know you need good eyes to see this properly. But the blue blocks on the bottom left are basically plots of worldwide pumped storage plants. There are dots as well, which might be a little bit difficult to see, but you can see that overall the range is between about $20, $25 up to $80 per kilowatt hour of energy stored. The difference between the blocks is between variable speed and fixed speed units. If we then look towards the right-hand side, and we saw some numbers as well from Babu earlier, we've taken the most aggressive numbers that we know of, which are from Bloomberg, and you can see, as has been mentioned, a decrease in the battery cost, and we expect it to decrease as well into the future. So batteries are certainly a part of the story, but you can see that there is a cost advantage which exists for pumped storage today. We don't expect the costs to go down dramatically for new build, which is unlike the other fuels that we've seen earlier. Nevertheless, what we are trying to do, and you'll see that in a moment, is bring more features to hydro. So to do more for the same cost. Just to show you this one as well, if there's anybody on from PNNL, you might recognize this study. It was done with the DOE. It's just a third-party study as well to show the differences of costs with different battery chemistries and then being compared to pumped storage. So again, very competitive form of storage. I'd now like to briefly, and I try and do it briefly because I know we're time limited, I could talk about this for hours, but just to say that there's a lot of advanced technology in hydro power plants today. And typically in the US, the kind of technology that you know is what we would call the first generation of pump turbine technology, of machines which can turn in both directions to both produce and store energy. And they were used typically with the fossil fuel base and the nuclear base to regulate the production. What we've seen since about 2015 is a big change. We've discussed already the rise of renewables and what that's starting to do, but there is very definitely a break between the first two generations of technology and the latest technology for several reasons. And I think in the US, you know this very well, but the energy transition for me happened in the US in 2016 and 2017, because that big pump storage fleet that we talked about suddenly wasn't pumping in the night anymore to accompany the fossil fuel plants and the nuclear plants. It was decoupled and coupled to intermittent renewables, because now the pump storage plants in the US pump the majority of the time in the day. So the transition's happened. And the other things that are starting to happen is that the machines are being started and stopped and cycled much more often than they were before. And for new build, we're typically looking at starts and stops of 6 to 10 to 15, sometimes even 20 times per day, when previously they were being started and stopped 2 or 3 times. And we're looking there to give machines which are capable of doing that for 40 years, because that's the typical design life. We're also looking at making machines more and more reactive, more and more flexible. You can see that there are ramp rates that we're looking to increase. There are transition times going from, for example, pumping or power absorption to full generation. We're able to do that now in less than a minute, from, for example, minus 150 megawatts to plus 150 megawatts in less than 1 minute. And equally, to start a machine up from standstill and produce 100% of power in less than a minute. It has been mentioned earlier by the other presenters, the fact that the business model is not always there. Very few markets today pay for that kind of reactivity. Whilst we do feel that going forwards, and we do see it in certain grid situations, that kind of level of reactivity is needed. A couple of other items as well on flexibility. We're looking to make our machines more flexible with a wider operating range. Typically for pumping or power absorption, that comes through variable speed. But otherwise, even in generation mode, we're looking to make the machines have a wider operating range. Here you can see as well, especially in the center, we're just representing machines with a simple diagram. You can see as well that inverter-based hydro is starting to happen, either through the double fed arrangement or the fully fed arrangement, where there's a full-size converter between the grid and a machine. That's starting to happen. There are machines online elsewhere in the world, not yet in the US. We do hope that it will happen. But they do bring additional benefits, and notably the one I mentioned before of bringing flexibility in pumping mode. I've probably covered this one, and I'll keep going just in the interest of time. You could always come back to it if you needed to. I'd also just like to mention where pump storage is hot in the world and why. It's often considered in other places, particularly in regulated markets where there are still combined utilities. In certain places, it's seen actually as a grid asset and not a generation asset. And that's helped stimulate growth. We can also see that there's a lot of pump storage being put in now where there's going to be a lot of solar. But I think if I really cut to the chase on this one, what is interesting is that pump storage is being built where there's a long-term visibility and a solid enough business case. So we're often talking about 20 to 25 years on the visibility, and we're often talking about a minimum price and a maximum price so that people at least have the hands around the business case. It was mentioned by previous speakers as well. What's the interest of stopping to produce energy if we're not being paid sufficiently well for ancillary services or others? And I'll just pull out one example. You may know it already, but the one in India recently, which I think is very interesting. It was an auction for 1,200 megawatts of renewable energy for 25 years with a peak and an off-peak tariff which were guaranteed. But the sort of trick on this one was the government said, we want 600 megawatts, so half of that capacity, to be firm for 6 hours. And in order to guarantee that, the winner did a combination of wind, batteries, and pump storage. And I think that's one of the ways forward, of course, with solar in as well. I've talked a lot about pump storage. I'd like to finish with an example of conventional hydro. And it's just to show you that the future, we've talked about with COVID and various things about saying it's accelerated the transition, or we're seeing into the future because we've had more renewables on the grid than fossil fuel. I think it's very interesting to have a look at Tasmania. So Tasmania is the island to the south of Australia. It has got a link to the mainland, a high voltage connection. And basically they have had days where they've run the wind, they've run the PV, and they've been taking energy from the mainland, 80% of production from non-synchronous sources. So we've been talking about this future inverter-led world and so on. They can run at 80%. What are they doing, though, with the other 20%? They've got the hydro, but they've also got a fleet of about 50 hydro units, of which 14 are able to spin in air and to provide a synchronous condenser function. So in order to ensure that 80% inverter-based generation will allow the grid to stay and stand up, they're using all the hydro machines that they can that can provide reactive power are doing that. With, of course, the benefit that when you no longer need the reactive power, those hydro units can generate energy as well. So if I just give you my sort of closing slide, hydro is renewable. Homegrown, for example, if I'm talking to the US audience, doesn't need exotic materials. It's dispatchable at scale, and I think this is an important point as well, in that in the future world we might have self-healing distribution grids and so on, but there might also be a need at some point to really push a lever home and get a massive amount of energy. That hydro can do. I've talked about it being storable, long-lasting, and other things, and the fact that it's competitive. So I hope, and I'll stop there, I hope it's been informative, and I hope that you can see that hydro really is an important part of the energy transition. Thank you.
Thanks, David. Obviously a topic that's quite close to my heart. Now I'd like to turn it over to Nick Miller, who will moderate the questions for this session. And I'd like to invite all of the panelists to open their microphone and video.
Okay, super session, everybody. And I've got quite a few questions that have come in on Slido. Just to reiterate to the audience, there's questions. You can see all the questions if you go to Slido and enter the ESIG 12 code and vote for some of the questions that push them up in my priority list. And I'm going to consolidate a few of these for folks. So I'm going to start with a question that's directed at Paul. And it's a question about the competitiveness of, there we go, right in front of the competitiveness of offshore, what's required, and there's a few other questions about squeezing costs, grand challenges for decreasing cost of wind energy. So maybe you can wrap that together, Paul.
Well, yeah, I should just first comment that there's a slide I usually use that I did not, which states simply that predictions are difficult, especially when they're about the future. But I'll give this a shot. I think there was a good indication of the potential for offshore wind that came out of Europe about 2 years ago, when there was almost a step change in the bid prices that they were getting out of the offshore wind, which dropped by almost a factor of 2. And it was really driven by the confidence and the removal of uncertainty from the construction process, from the actual large construction vehicles, and working with time windows and weather windows. And when that risk was taken out, there was a huge reduction in the cost of offshore. So whether that's going to compete with land-based wind is always a difficult question to ask, because there's always an additional cost of that foundation, which is going to be more expensive. And improving the technology of the machines themselves on land and offshore will probably go hand in hand. So it's hard to imagine that offshore will reach parity, yet it does have a higher resource. There's more energy available. The value of that resource may be better because offshore can be located very close to load centers. So I don't know if the prices will become equitable. I think the thing that we're most eager to see is the cost of the floating offshore come down to where it's competitive with the fixed bottom. I think that is certainly possible. I think we have a lot of optimism that can happen, but floating offshore is still brand new. No one has even converged on a single architecture for the floating foundations at this point. So there's a lot of costs yet to be driven out of that technology. So I hope that's helpful.
Paul? All right. There's a couple other cost type related ones, but I see my occasional partner in crime, Simonelli's question has floated up to the top, and certainly this is a key point for everybody. I'll paraphrase a little bit of John's point. Becca and Paul and all of you have been talking about some of these great functionalities that we can get, and yet essentially, aside from spinning reserve and reg, the markets have not followed to provide incentives to get these functions from any of the 4 technologies. Do you have any opinions on what's needed to shift the dial away from doing same old? I think that's open to all 4 of you.
I mean, I could jump in. I think Paul touched on this as well, but right now there's no economic driver for that in the markets. The way that solar plants can make the most money is to produce as much energy as possible. A lot of those plants are getting some form of, under some form of PPA or relying on renewable energy credits or things that all incentivize them to maximize energy production, and that's far more lucrative than curtailing some amounts of their available for ancillary services. So until there's an economic driver, or until we have longer durations of time where we see wind and solar at such high penetration on the grid, I think it takes one of those things for us to drive that forward.
If I could I could add a comment as well. I would say it's not an easy question, and I think people have been wrestling with this for some time, and it might still take some time to play out. But if I could give you one example coming from Israel, Israel's an electric island, and they're wanting to transition from fossil fuels or put a significant amount of renewables in at least, whilst maintaining their grid, which you can imagine is an extremely important factor for them. They were quite inventive in the way that they've done that, and they put incentives in. I talked about these fast transition pump storage plants. They pay for availability, they pay for capacity, and they pay for fast reactions. And as soon as it's paid for, of course, we'll provide the technology that can do it. I'm sure we could all do that. But it's just to get the right incentives in there. Israel's potentially shown a way. I mentioned the Indian one as well. But it's really to take these case studies and try and get them to the decision makers and get the right market designs.
That's fertile ground, and obviously John and I care a great deal about it. It can also consume an entire day of workshop, I think. Becca, this one's directed at you. I'll come back to this one for Babu as well. But so somebody is pointing out that the EIA has been consistently off the mark. How are you doing? I think that you is directed at DOE CETO, but maybe it's more broadly.
Right. Yeah, we look at a variety of scenarios, and when you're looking at projections for the future, it really depends on what you're bearing and what you're looking at. So we certainly have scenarios that show that solar could be, well over half of electricity generation by 2050 under certain conditions. And I think that shows the wide range of possibilities. To some degree, there's some, competition between solar and wind, and it'll see, who gets cheaper faster and more attractive in terms of which ends up being deployed in larger shares. And other big factors are just how cheap and how much energy storage deployment we have and how fast we see electrification. I think those are some of the largest levers that determine, and influence these projections. What you're assuming about energy storage, electrification, and then wind versus solar pricing. We also fund the National Renewable Energy Laboratory to do an annual technology baseline that provides cost numbers and associated projections for renewables in addition to what the EIA projects. But those baseline cases trade off year to year on wind and solar, and which one's going to grow more quickly going forward.
If I could. I think EIA, to be fair, is highly constrained. I mean, they do have to follow a certain set of rules on what they're allowed to project into the future in terms of cost projections and of the technology. So if you look back historically, they've never been able to predict the correct penetration of renewables. It's always been low, and that's because they have been constrained by their own rules from actually hitting the mark for how much cost reduction was going to happen. So you just have to take what they have to offer for what it's worth. They can't do really high change scenarios. They're just not able to do that.
Thanks, Paul. Well, I'm going to exercise my facilitator's prerogative and pull on this thread just a little bit further relative to what's cheapest in a problem that I think all four of you have observed on different edges of the knife, and that is that an awful lot of current planning tools that are basically designed and being used to make long-term projections and plans do not seem to be doing a good job of valuing technology diversity. So today, in this run or this set of planning, solar PV and lithium ion end up at the bottom of the optimization curve. And everything that's going to get built, and I won't make fun of any particular ISO, but you probably know who I'm talking about, for the next decade is now going to be PV and batteries and nothing else. And David at Hydro, sort of sees that and says, look, we are competitive, but your optimization software isn't valuing these other things and isn't valuing diversity, how do we recognize what your grandmother always told you, which is don't put all your eggs in one basket?
Well, I think the ISO that you're mentioning probably forget sometimes that they were using 3 gigawatts of pump storage flat out for 48 hours, generating and also pumping so that the gas units could be kept online. So maybe the way to do it would be to take things out. I think we do struggle with models anyway, because the models do struggle to get the black swans or the out of the. We're often averaging things out, so I think that's one of the difficulties with models. You don't get the extreme events. And then maybe one way now is if we do manage to understand how today's grid is working, can we take them out as is a sensitivity analysis?
Yeah, and there are a number of factors that aren't well captured by models, and of course they can't keep up with policy changes, but they also don't well account for how difficult it can be to finance and bring online a large capital project, and they have very fixed time horizons, which may not align with realistic assumptions for lifetimes of technology. So there's lots of challenging factors, and I don't think anyone is advocating relying on those models to really predict the future.
Right. Well, David's got technology that lasts for 100 years, but very hard to get a model to value that, even if you reckon. Okay. Well, we'll leave that one beside. It's obviously one of my favorite topics. Babu, we got a couple of technology questions directed at you. You see this one, the value of AC versus DC coupled BESS?
Well, I think it's an interesting question right now. If you look at all the battery storage that is being deployed, it's in the distribution grid or some transmission applications starting to become real. So those are all AC coupled systems. The question is, where do we go? What is the difference between AC versus DC coupling and where things happen? I mean, if you were to look for a future where you have lots of microgrids, there's a potential for interesting options for DC coupled systems. But currently, you look at all the deployments that we currently have, it's all in the distribution grid or on the transmission grid. Those are the things which are going to be in the big systems. That said, I think, if you take a long-term view where you have renewables and others coming on a large scale in the 50-60% level, then how much power electronics and converters will you have in the grid is going to be the issue. What are the costs of the converters? And then, AC versus DC is all going to be application driven, very needed. Right now, maybe 20% of electrons go through some converter. But as you go into the future, maybe 80-90% of electrons will go through a converter. So the cost of converter technology will become hopefully a lot cheaper than where we are today.
I think I might say, and I see Becca getting ready to chime in, I might also interpret that question. I know that something on the order of half of the utility scale PV projects going forward by the biggest renewable developer in the U.S. are hybrid with batteries. So you have PV and batteries. That's could also be behind this DC coupled question. I wonder if Becca's got any thoughts on that.
Yeah, I think that there's a lot of factors at play, and it's a tricky question, and there have been incentives that have impacted some of these to date, and it depends to the extent to which how we're going to operate plants and how they're incentivized in the market. So I don't think there's a clear answer. Our cost modeling still shows that DC coupled systems should have cost advantages that may help them in the end, even though they don't have the same performance options.
All right, we're just about wrapping up. I want to get to, there's two last questions. One's a real, it's a quick one for Paul, and if you could provide that Nature paper reference, that caught my ear as well. And then I got a question. Oh, go ahead, Paul.
I'll just say it's in science.
Science. Okay, that's important.
The title is Grand Challenges in the Science of Wind Energy.
Okay.
Simple title, easy to find.
Sounds good. And then I'll wrap with David. There's a question here about retrofitting existing big dams. Somebody asked about the Columbia River, and I think that applies to others with taking large-scale conventional hydro projects and turning them into adding or changing out the generation to have pumping. What's the feasibility? What do you think about that?
I think if we talk about retrofitting the infrastructure, so adding in potentially new units which are able to work in both directions, that would work. It's relatively expensive because there's some civil works to do as well. If we talk about retrofitting just the machines themselves, it is something that we've looked at, but it's not so easy to do because typically if we go from generating to both pumping and generating, the machines have to be set deeper into the ground to avoid cavitation when they're pumping, which would destroy the runner. So normally we would sit them deeper in the ground, which therefore means that it's very difficult to actually change one out without changing its altitude and therefore, destroying a lot of concrete around. It is an area that we're looking at, and there may be one or two tricks that we could try, but it perhaps would be simpler to give you a simple answer. It's to use the existing infrastructure and add something in, as opposed to trying to change something, the equipment itself.
Okay. Super, that's good insight. Well, I think we've used up our time. We did pretty well getting through people's questions, and maybe I'll turn it over either to Charlie or Alejandro to make it a wrap, both on the session and I guess on the fall workshop. Huh?
Thanks, Charlie. I think it's over to you. Thank you. Let me thank all of the panelists again on behalf of all of us.
Okay. Yes, let me add my thanks to Alejandro's. I think the session offered some great insights into the future outlook for renewable energy and energy storage technologies, and I hope it's provided some stimulating thoughts for everyone. This is the last of the 12 sessions of the Fall Technical Workshop, and I really hope everybody found something of value in the variety of topics presented. We'll resume our regular monthly webinar schedule right after Thanksgiving on December 2nd with a webinar on the changing concept of resource adequacy with the changing resource mix. Touched on that a little bit in Paul's presentation today. The information is posted on the ESIG website under the scheduled events, and you're all invited to attend. So thanks again for your participation. Stay safe, and we look forward to seeing you the next time around.
Thanks, all the attendees.
Thank you.